No. Third from above. Third one. Yeah.
Good afternoon, everyone. So I'll be presenting a paper which I have made a year ago. And actually, I opened this paper to Ma'am Anniversary, if you can remember way back then, that I was confused with the title because it's actually a combination of two parameters. So, well, anyway, it's not yet published, but it's already done. So, I'll be presenting to you fragments of my results here. Okay. So it's chromatic numbers of the equitable dominating sets complementing graphs. Okay, so if we think about graphs here, regardless what would be our point of view on the application of what we studied, it's up to the networking or connections. So here in my piece, it's actually something I have created out from my experience. Okay, so here, if you notice, this is a graph, so I focus on two parameters, the domination and the chromatic part of the graph here. So these are just fragments, which I would be thinking that maybe a domination could be applied to these different disciplines. We have finance, computer science, medicine, networking, and other applied sciences. Okay, so all throughout, note that the history, the domination problem was studied from 1950 onwards. But as we all know, its rate of research has boomed throughout the ages. This is the reason why because there was, I have an experience before that when I traveled in Manila, my friends who studied UB asked me what is the country known for number theory? So I just answered, oh, maybe it's somewhere in India or in America. But when they asked where is graph, I just answered MHO-IMT. So this is the reason why I'll be presenting this paper. So here, this wireless networking, which is the domination. So maybe I should be reflecting on some paper which I have read before regarding on the domination applied to computer networks, like how many routers you have to use in order for you to have a maximized connections of wireless throughout computers. And so I have thought of maybe I could apply some connections regarding on the ratio of routers to computers in such a way that some compatible computers may not be adjacent to each other. So we'll talk about that later. I'll just get the gist of it. Okay. Okay, we say that D is the dominating set of G if we can find a vertex. We can find a vertex in that dominating set in such a way that we have also another vertex outside from that set to where they're both adjacent to each other. Okay, so, and the cardinality of that set is what we call the domination number. Okay, let's consider this example. Here. Okay, note that we can find, anyway, this is not unique. This is not unique for a selection of vertices for us to create that dominating set. But since I have mentioned that we focus on the minimum cardinality, so I'll just present to you what I have selected during my study. Here, note that if I pick A, its neighbors are B, C, D, and H. Also, if I pick F, we have neighbors like B, G, and E, which implies that since if we have the union of those neighbors, that set containing the neighbors of A and F, we have the equality, which is the vertex set of G. So therefore, that will be considered as our dominating set, which simply implies that the domination number is 2. Okay, so one of a type of a domination number, dominating set, is the equitable domination. Okay, it was studied by Deepak in 2011, and in 2012, I read a paper. I read a paper made in 2012 regarding unconnected equitable domination in graphs. Also, in 2015, we have created a perfect equitable domination in graphs. So, what's equitable dominating sets? So, a subset is called an equitable dominating set if we have a V from outside that set, we consider, in such a way that we found a vertex from that dominating set, and such that the absolute difference of their neighbors should not exceed 1. And its minimum cardinality is what we call equitable domination number. Let's consider this. Okay, if I pick A here, note that it can dominate B, H, D, E, and F. Sorry, my bad. Okay, observe that A can dominate B. However, if we compare the numbers of neighbors here, the numbers of neighbors for A is 4, but for B is 2. And take note on the definition that the absolute difference of their neighbors should not exceed 1. So therefore, I cannot compare A and B. I'll just include instead B as part of the dominating set. And so with H, since the number of neighbors for H is 2, which is way far from the neighbors of A. So I'll include H. But there's no problem if I select if I don't include D, E, F. Yeah, D, E, F. Since the numbers of neighbors of A and the numbers of neighbors of B are the same, so definitely the absolute difference is 0, which is less than 1. Okay, so, however, note that I have picked B, which simply implies that B could dominate C. But note that the numbers of neighbors of C is 4. Therefore, I need to include C there. Same with G. Oh, I'm sorry, my bad. No. I'm still correct. I'm still correct. I don't have to include G. Okay, so therefore, the domination number is equal to 4. The equitable domination number. Okay, so here, let's go to a chromatic number. So we all know that this has been originated from, I think, in the coloring of countries in a certain map. So one famous example is a 4-color problem. And in 1912, George David Birkhoff introduced the chromatic polynomial to study the coloring problem. Oh, okay. So in 1990, Arugay studied the path chromatic number in graphs in her dissertation in Ateneo. So in 2015, we have made a graph. We call that one as chromatic. It's an automark graph in which we created some generalization of a certain type of graphs. We studied this chromatic number and edge chromatic number. Okay, so a chromatic number of graph denoted by that symbol, chi of G, is the minimum number of colors used to color certain vertices in such a way that two vertices adjacent to each other must have different colors. Okay, let's take a look into this one. Okay, I color A as red, so therefore I cannot select B and its adjacent vertices as red. But however, I can select C anyway. F, on the other hand, cannot be colored as red because it's not A. So I choose yellow instead. They're not, anyway, D and F are not adjacent to each other. And I can color this as blue. I know we can. And also, oh, I'm sorry. So therefore, the chromatic number is 3. There are 3 colors used during the coloring of vertices. So here in this study, I'll just combine the 2 parameters. So I form a dominating set from that graph, and here's the definition. If the cardinality of the complement of the dominating set is odd, then I follow the same chromatic rule. If it is even, then that's the cardinality of the complement is the number of colors used to color those vertices, regardless adjacent or not. Okay, let's take a look into this one. This is how I evaluate equitable dominating set of a graph, which simply implies I chose A and E to be equitable dominating set. Hence, our F there is, the cardinality is 5, which is odd. So I have the color red here. So since F is not adjacent, so I color that as red as well, but those adjacent vertices can be yellow. Excuse me. So I use a different color for B. Anyway, this is self-explanatory. So therefore, my equitable chromatic number is 3. So consider another example here. That graph, yeah, this is my equitable dominating set, which is 4, since this is even, so therefore that is equitable domination number. No, it's equitable chromatic number, I'm sorry. So this study aims to answer the following goals. Is it possible to determine the chromatic numbers in the equitable dominating set complement in graph? And what are some necessary and sufficient conditions for graphs in the given parameter? And what could be some applications of the study of the equitable chromatic number? Disregard that, by the way. I'll just show the objectives and significance of the study, and this is my motivation. When I was asked by a student in the University of the Visayas, the school I taught before, regarding on what could be the application on segregating chemicals in such a way that we have to hire guards to guard buildings. And that's all. Here are my results. And that's my references. Thank you.
We are now open for queries. Thank you for the presentation, sir. We can still have one question. Yes.
Chromatic numbers are usually used in graphs, but in your case, you are using the chromatic numbers in equitable dominating sets or in boosts.
In the complement. So in a certain graph, I have to get the dominating set first. So the complement of the dominating set is why I apply the chromatic number.
So it's only a set, not the boost. Or you include the adjacencies.
I only took the set. So let's consider this example. Sorry. Okay, that. Let's consider this example instead. Yes. So I'll just consider it outside from the range of dominations.
So we're gonna have to stop the question and answer portion as we do not have the time anymore. So yes, please approach the
I'm
presenter.
open for any questions.
Yes. We award the certificate of appreciation appreciation to Mark L. Guy for having presented his paper in this conference. So we have
Picture one.